University of Messina. I presented this contribution in collaboration with other colleagues. I would like to specify that this contribution comes from a recent collaboration established between the University of Messina and the Politecnico di Torino in the field of fracture behavior of formed concrete. I would like to start framing this contribution within the wider context of cellular concretes, because formed concrete belongs to this class of cellular concretes. In particular, these variants of concrete materials have different advantages in comparison with normal weight concrete, ordinary concrete, in particular better thermal insulation properties and acoustic absorption, fire resistance, good workability, and obviously lightweight properties that makes them particularly effective for realization, like for example in infill panels or non-structural partition walls at the very low density ranges. And formed concrete is created by, is a composite, is created by a mix of water, cement, and fine sand, possibly other mineral additions like fly ash and silica fume to increase the mechanical strength. And the foam, which is a preformed foam, can be created with different surfactant or foaming agent that can be protein-based foaming agent or synthetic-based foaming agent. Foam is obviously a solution of water and surfactant that are mixed together and expanded with air. So I just want to, because this is an experimental work, so I would like to specify how did we generate the foam, how did we implement it in our specimen, and then I will discuss the result. To generate the foam, we used a very simple and homemade foam generator, which is actually composed of channels 1 and 2, which conveys water and surfactant at a specific concentration of 5% that are mixed together. And there is also from elements 4 and 5 a compressed air at a pressure of 3 bar. And then these elements are conveyed through the channel 6 and to these rings. There is a turbulent flow that creates the final foam, which has a density of 85, 80, 95, and 90 grams per liter. So, introducing the preformed foam into the cement and water, we obtained the formed concrete. And our previous investigation, started at the University of Messina, was focused on the role of some parameters in the preparation of formed concrete samples. In particular, we investigated the curing condition, and we noticed that the curing condition had a very key role in the final mechanical strength of formed concrete. We prepared a specimen left in air, cured in air during the 28 days. Other specimens were submerged in water at a specified temperature, and other specimens were wrapped in a cellophane sheet, because this is a common practice adopted in the precast industry to prevent evaporation of water. And we, for example, noticed that since the above mentioned advantages like thermal insulation, acoustic absorption are particularly evident in the low density range, we explored low densities in the range 400 up to 800 kilogram per cubic meter. And we noticed that in this range, the mechanical strength, in this case the compressive strength, was almost linearly increasing with the dry density. We explored the effect of these different cements, and we noticed that the foaming agent, the liquid that we introduced to create the foam, has an important role and determines a very different mechanical strength, which for a fixed water to cement ratio. So the water cement ratio should be adjusted depending on the type of foaming agent employed. We obtain a comparable mechanical strength using the synthetic based and protein based foaming agent, but with the totally different water cement ratio, in particular 0.3 and 0.5. This work was carried out for a particular variant of foamed concrete that incorporates a viscosity enhancing agent, and that makes foamed concrete particularly appealing for very efficient production process. In particular, we called this new foamed concrete extrudable foamed concrete because introducing a particular viscosity enhancing agent we obtain a very high cohesion and viscosity at the fresh state. If we compare the two images, a classical foamed concrete with this new material, we notice that the material is able to keep its shape at the fresh state. This is the fresh state of the material. And we demonstrated this particular advantage by simulating an extrusion production process, like with a very simple hardened cubic specimen that pushes a fresh state paste. But we noticed that the fresh state paste did not expand laterally upon pushing the specimen. And this was also demonstrated by other tests that we performed with the robotic arm. And in fact, we are working on this, based on these encouraging results, we are working on this new field of application of foamed concrete that can speed up the production process in a construction field. Previous investigations were concerned with the possibility of increasing the resistance of the foamed concrete through the addition of fibers or through the placement of bidirectional grids, which is convenient for example, partition walls in residential buildings. We noticed that there was not so detailed investigation in the field of fracture behavior of foamed concrete. We explored the current literature, so we were motivated to undertake this task, and in fact we prepared some specimens in collaboration with the Politecnico di Torino, and our simple notched specimens as can be seen here. We followed the Japanese testing standard, which is in line with the relevant procedure to determine the fracture toughness. In particular, the notch height is 0.3 of the beam depth. We placed some, we attached some supports underneath the notched beam to measure the crack mount opening displacement in displacement controlled three-point bending test. And this allowed us to evaluate obviously the fracture energy and the flexural strength of the different classes of foamed concretes. In particular, we focus on this parameter because this seemed to affect the mechanical strength in static tests and compressive tests. So we were motivated to explore also this fracture energy or fracture behavior depending on the curing condition. And in fact, we prepared a half of the specimen, just a small number of specimens, 8 specimens, but we left curing in air, and the other half curing in water curing at a specified density of 800 kilogram per cubic meter. And we determine the flexural strength, the fracture energy, and the compressive strength on the hulls of the broken specimen, according to the Japanese testing standard. Surprisingly, we noticed that the curing condition have a very strong effect on the fracture behavior. In particular, the fracture energy computed to the formal reporting the standard was more than 200% higher in the specimen cured in air compared to the specimen cured in water. And the flexural strength was more than 100% higher for the same class of specimen. These are just two pairs of curves for two pairs of specimen cured in water and in air, in which we clearly notice that the totally different behavior of the load versus crack mount opening displacement curve. So, one encouraging thing is that the behavior exhibited significant post-elastic branch in the which confirms that the behavior is not brittle and can be enhanced and improved by the introduction of, for example, fiber, as we did in our previous investigation. And the two, we try to explain this different behavior in the two curing conditions, and we performed some, we took some images with the field emission scanning electron microscopy. Images taken across the crack surface, so where the crack started and developed. And we notice here that the image confirmed that the density is similar, comparable, so we can see that the bubbles, the pores are of comparable dimension in the two cases, air curing and water curing. But also we notice a more distributed crack pattern in the air curing condition with respect to water curing condition, and this is obviously influenced by the interaction between the cement matrix and the foaming agent in the two cases. And the distribution of pores obviously influences the crack initiation and development. And in fact, we also notice across the surface from a macroscopic point of view that the surface was more, the roughness of the surface was more evident in the air curing condition in comparison to water curing condition, which seems to justify that the crack should follow a more intricate path and the fracture energy increases accordingly. And going towards a smaller scale of observation, we recognize different hydration products in the two cases. And in particular, in the air curing condition, we notice mono-oriented stripe shapes typical of flat crystals, probably portlandite. And in the water curing condition, instead, we observe the bidirectional shapes like flower crystals. And this seems to indicate a different interaction between the foaming agent and the cementitious matrix in the two curing condition. We are going on in this direction. Obviously, this is just a preliminary experimental investigation. We would like to extend the investigation by covering higher dry densities, higher than 800 kilogram per cubic meter. And we would like to incorporate in this material other mineral additions like silica fume, or also other mineral particles like biochar. And we would like to extend the investigation also to other testing setups, different from the Japanese testing standard. Thank you very much for your attention.
One question.